Welcome back. In the last lecture, we talked about the active faults, and we stopped at while discussing the 1995 Kobe earthquake. Now, let us move ahead, and I'll start with this slide where we were talking about that how the surface manifestation look like. Okay, and then previous slide, if you look at, we talked about that how if there is a subsurface displacement, how this there is a manifestation on the surface. So we talked about the fault scarp, which you can see here, and then this is the displacement here. So net displacement can be taken up between these two units. Okay, so let us move ahead. So this was the one of the devastating earthquake in Japan in 1995, and the picture which you are looking at here is the surface rupture of 1995 Kobe earthquake. We will go into the details of this. Now, as I told during that in the previous lecture also, that Japanese government, what they did, they preserved this surface rupture, and they made or they built the museum on this fault to create an awareness. Okay. So this is extremely important because for the society, because this is whatever the whenever there is a big earthquake, there is a lot of damage, and a lot of people are at risk because of the this sudden catastrophic events. Okay. So people should understand that what exactly happens during the earthquake, and how there is a surface manifestation, and how geologists looked at it actually. So like as I was talking about, that if you put any structure on the active fault without having understanding that what sort of movement it will be, and first of all we should avoid putting structures on the active faults. But even though there is no other alternative, if we have to cross the structure and we have to put the structure on that, so we need to understand that what will be the movement and what type of displacement it will result in when there is an earthquake. So this is an example which shows that there was if you look at this wall here, this wall got displaced at the time of the earthquake in 1995 Kobe. Now, if we in a broader sense, if we look at Japan, the Japanese islands, okay, they are the result of the ongoing subduction between the Eurasian plate, Philippine plate, and Pacific plate and Philippine plate, and the American plate and Eurasian plate. Okay. So this is what is the broader configuration of the tectonic setting of Japan. Now, if we move ahead, what happened in 1995, that the rupture started, and the main earthquake was along the MTL, median tectonic line. This is very much similar to San Andreas fault system with the right lateral strike slip motion, and the earthquake was triggered somewhere here, and the rupture propagated on either side, and the extensive damage which was been observed was at Kobe because of the soil conditions and all that. Okay. So this fault they named as a Nojima fault. We will see some surface manifestation of this earthquake, which Japanese people measured after the event. So this passed through. So if you look at this point exactly, okay, this is what the two islands are been connected through this bridge. Okay. So this bridge also, the piers of these two bridges, okay, this side and this side, the fault process in the middle, and they were also been displaced little bit. Okay, so the earthquake was of magnitude 7.2. It occurred on 17 Jan 1995, caused severe damage to Kobe and the towns in the vicinity of southwest Japan. The rupture propagated laterally in both directions of the epicenter, as we have seen in the previous slide. Okay. the Awaji Island, the rupture was seen in the Awaji Island, okay. It was more prominent, and that was along the Nojima fault, and it was been traced for almost 10 kilometers. The Nojima fault is northeast southwest striking right slip fault, right lateral strike slip fault, and this is formed due to the east west compression stresses, okay, stress field, which is attributed to the plate convergence with the West Pacific plate. So, I will just briefly talk about this. Now, what was the most important, if we, in terms of what we should look at, is the surface faulting. If you look at here, okay, surface faulting revealed that there was a maximum right lateral displacement of 1.9 meters, along with maximum vertical displacement of 1.2 meters. So, the fault moved laterally as well as it resulted into the vertical displacement also. So, the land was been moved laterally along the strike by 1.9 meter, and around 1.2 meter it had a vertical displacement. So, this is very much important to understand when an earthquake occurs, and we need to know that what type of fault it will be and what type of displacement we will experience. Okay. Around 5,000 people were been killed, and then around 1 lakh houses were been destroyed. So, this was the alarm to Japanese government that they need to take up this type of studies in more seriously, and that what they did actually. So, after 1995, maximum studies were being carried out in terms of identifying the paleo earthquakes and in understanding that how individual fault is behaving and what will be the expected recurrence interval in future along those particular faults. So, this is what they identified, that there was slight shift between the two piers of the bridge, almost like and there was an uplift also of almost 20 centimeter or so. Okay. And then suspension bridge was been displaced by almost 1.3 to 1.4 meter right laterally. So, this is the important part which I have been talking about, that we need to know that where exactly the fault passes. Nothing happened to the bridge, but there wasn't severe damage in that area. So, this is the satellite picture which shows the pattern of damage after and before. Okay. What happened, if you see here, okay, that this was the damage area which was been covered. This is Kobe area, and severe damage, this you might have seen in many books. This photograph, the bridge was been extensively damaged, main bridge, okay, and these are the photographs of that. Surface rupture, coming to the surface rupture, this was the trace which was been identified, and we will see the close up of this, how it looks like. Okay. This is something like that. Okay. So, you have a vertical motion here, and one close up of this one I hope we have. Okay. And if you look at this part, this is an agricultural field or the agricultural boundary which was been displaced. This is the boundary coming here, and this is over here. Okay. So, this is the rupture here, this one. So, the fault moved like this. Close up of that, you can see the rupture on the top of the surface, and what they found was the striations. Okay. And this photograph is from the edge of this one. This photograph has been taken from here, viewing like this. Okay. So, this what it shows is the striations. This indicates again that in which direction the fault moved. Okay. So, if you see clearly here, there are very fine striations on the polished surface which was resulted because of the movement, and the wall moved like this. Okay. So, direction of the movement is like this. Now, if you compare the piercing point, like this is the the agricultural boundary here we are having over here now. Okay. So, this point and this point. Okay. So, you have an vertical displacement also and you have lateral displacement. So, the slip, right lateral slip was around 1.9 meter and the vertical slip was almost like 1.2 meter. So, it moved right laterally and it moved vertically also. Okay. There's another view of that surface rupture which you can see here. Close up of that one. So, several small scale fissures were also developed along with that, and most common phenomena which is what we call as a secondary phenomena mostly seen in or observed during an earthquake is liquefaction, okay, and lateral slip. So, lateral spread or lateral slip of the land is also another commonly seen effect, and those are secondary effects. Okay. So, other than the faulting which is resulted on the surface or the fault scarps, okay, which are seen on the surface, because of strong ground shaking you will be able to observe or experience the landslip, which is if you are having a very low angle slope, then also you can have that, and then the liquefaction. Okay. So, this is an example which you see here is of the lateral spread. In a proper sense we can say is a landslide. Okay. And then we have liquefaction. Okay. So, along the fissures we will have the liquefied material which is coming right up to the surface, and this is extremely dangerous because if you are having a structure sitting on such soil strata, then that structure will collapse because the soil will lose the shear strength. So, in India in particularly, if we are having a big earthquake or large magnitude earthquake in Himalaya, a lot of problems will be faced in terms of liquefaction in the Indo-Gangetic plain because we are sitting on the loose soil. We have the very and the water table is also very low. Okay. So, we will have liquefaction problems in the Indo-Gangetic plain. So, they preserved this whole rupture in a form of a museum, and they also took this house which is now a part of the museum, and you can see this, the rupture is going over here like this, and then there is a displacement which can be seen over here. Okay. So, this boundary wall got displaced, okay, right laterally. So, if you can put here like this, then it goes like that, okay, and then here also. So, fault runs here. So, you are having the movement like this over here. So, this is important, like we need to know that where exactly the fault goes. So, we should avoid putting structures on such fault lines. There is a close up of that, another close up of this one. You can see the offset of the boundary wall. Now, what they did was they created. So, this is the museum which they have created after this. Okay. So, this part goes into the museum. So, they excavated a trench which shows the sectional view of the fault, and to show the people. Okay. So, they have this is a rupture coming up, and this is the sectional view, and then this is on the horizontal view of that. Okay. So, they dug this and they have preserved. So, they put the glass on this one, so the people can walk down and move on the fault itself and try to understand then what exactly happened. Okay. This is another very good example which has been preserved again in the museum, which shows the small drain, okay, in the farming land, okay, which got shifted. So, these are the piercing point, two pink and then blue, which shows the points which were the surface which were together before the event. So, this is what the people do, okay, and try to look at what happened in 1995 Kobe earthquake. So this is a very small movie which I hope it will play. So this is a small video which I took when I visited this place, where you can see the whole rupture, how it has been preserved. Okay, so this is extremely important for all of us to understand that how rupture looks like, and what happens during an earthquake. Okay. So moving ahead, this is another one which they have created, which again gives a very good idea about that what happens during an earthquake. So if you carefully see here somewhere, you will be able to see that what happens during an earthquake. The land is coming up, and then there is a displacement on the surface. Okay. So this is a model which they have created, and they have tried to make people understand. You can see the wall which has come up here now, okay, whole. So this is what happened during large magnitude earthquake in Japan. So this is a part of their exercise, which usually they have done for some earthquakes. So this you can see now how the displacement will occur. Okay, so this is multiple events. Okay, not the single event; it will be multiple event which will occur, and this is the person who was behind this, actually Takashi Nakata, who created all this idea, and then he approached the government to do that. Okay, so now there is another, like these are the other four signatures of the earthquake, which is again preserved, and they have not disturbed at all. Okay, so this is a recent photograph which was been taken, where you can see the stairs have been displaced over here. So you can see the displacement over here. The stairs boundary should have gone straight, but it is displaced along this line. So these are some very important aspects which we should have in most of the countries, and many countries have followed this and tried to create awareness amongst the people. This is extremely important. Okay, so there is a shift here, and this is a close up of that one. Okay. Now liquefaction and lateral spread was very common in the areas, in the coastal zones, where they reclaimed the regions. Okay, so this is the reclaimed areas where they had a massive liquefaction. So all white spots which you see here are the liquefied sand which came up through the sand flows. So in the harbor areas, you can see the liquefaction problems which they faced, and then sort of in potholes, or we say the sand blows, which were been created because of the liquefaction. Now associated landslide. Okay, there is another problem which is commonly observed after each earthquakes. Okay, or during an earthquake we will have these problems which we need to face. Okay, in the hilly areas mainly. So this is another event which was magnitude 8, Nobi earthquake again in Japan, which shows the fault scarp over here. The photograph is not so good, but you can see at least the displaced area here. So it was in 1891. So this photograph was been taken in 1891, and then you can see the recent one. Okay, so still that surface rupture is been preserved on the surface. No doubt you can see the road which is going across it, but the scarp is over here. This is the scarp which you see in this photograph here. But those faults are well marked in Japan. Another photograph of which was been taken by Professor Okada in 1974. The previous one was in 1969. The same guy, he's taken the photograph of this one. Okay, so how the things have been modified and still it exists. So it's almost been modified now here. Okay, so fault runs here. Okay, so this still you can see the scarp over here. So the question is that can you identify the fault, active fault in this? Yes, of course. If you understand that the landform displacement and the morphology of the fault, then you can identify the active faults, and that's what we have been doing in India along Himalayas and in Kutch region. Now coming to the reverse and thrust faults, here what we have learned in the previous course also, and then during this the couple of lectures before, that the hanging wall will move up with respect to the full wall, and mostly this type of deformation has been seen in the compressional tectonic environment. And the best example if you have to look at is along the Himalayan zone. Okay. So this is another photograph of the active fault, aerial photograph, which has been taken, which shows the trace of the thrust fault or the reverse fault over here, which has displaced the young landforms. Okay, and that what would we do is we try to look at that whether there is a displacement of the young landforms or not, and try to, with an experience, we try to differentiate or delineate the fault scarps, and because similar erosional features can also give similar features on the surface. Okay, so that has to be negated, and then we can say that okay, fine, this is an active fault, this is not an active fault scarp, something like that. Okay, so we need to have the experience to identify such things. Okay, again the fault trace has been shown here by the arrows, where you can see this dark greenish portion is a scarp, and which has displaced the surface. Okay, there is another example of 1995 Chichi earthquake. Okay, where you can see that the fault passed through the playground, and the running track was been warped. Okay, and this is a typical fault scarp which one can expect during the reverse fault or thrust fault earthquake. Another photographs of the same, you can see the warp here. So 1999 Chichi earthquake in Taiwan. And coming to this, okay, this is another one which occurred in 2005. Okay, now there is a small story behind it, that this fault scarp which you see now here, okay, was been identified by the professor which I was showing in the video, Takashi Nakata. Okay, he identified in 1999, named that as Thanda fault. Now this report was been submitted to the Geological Survey of Pakistan, and he categorically mentioned that this fault may trigger a large magnitude earthquake in near future, but they didn't believe him, because they said, oh fine, this is only 16 kilometer or 13 to 16 kilometer long fault, how it can trigger a large magnitude earthquake. But based on his experience and the work which he has been carrying out in Japan, in India since last 30 to 40 years, he mentioned that. Okay, and this what we experienced in 2005 Muzaffarabad earthquake. The same fault ruptured, and we had a lot of life loss. Okay, so this is a fault scarp which you can see, and most of the flat lying structures are the houses which were been raised to the ground during an earthquake. This is an hanging wall, this is a foot wall here. Another example from India, this where we have been working as a part of the project sponsored by Ministry of Earth Science on active fault mapping in Himalaya. So this is another scarp similar to what I was showing in Pakistan, Thanda fault. This fault we have named as Hajipur fault, and this is this exists on the left bank of Bias River. So you can see the uplifted part here. So there is if I just put a profile here, it will be something like this. Okay, so there is a fault here which has moved like this. Okay, so this is an hanging wall and this one is the footwall. Now, if you look at the question comes that why this guy has put the house on top of this, okay, because he is not aware of the active fault, he is not aware of, he might not have experienced the earthquake. Of course, because the earthquake's recurrence may vary from 500 years to 1000 years for large magnitude earthquake of maybe magnitude 7.8 or around 8. So, the lifespan of the human is not so much, so people keep on forgetting. Okay. So, during this decade or maybe in the past couple of decades, we have not experienced a major earthquake in Himalayas. Okay. Our study suggests that there was a major earthquake in 1500 AD, okay. So 1400 to 1500 AD, it was somewhere around that, and then so we have not experienced any earthquake after that in this region. So probably because of the less awareness, people have built the houses here. Okay. So when we were doing our work in this area, people asked that there is no problem. Okay, only one house has been built on this fault, but the point is that slowly more people will come around and have their houses here. Okay, so one guy came, another guy will come, and then they will have more houses on this, but this should be stopped. Okay. So this is in fault scarp, Hajipur fault scarp, and fault runs somewhere over here. Okay. So coming to the strike slip, as we have been talking about the 1995 Kobe earthquake, we will have the lateral movement, and if we are having the oblique component clubbed with the strike slip, then we will see the vertical displacement also. So geomorphic markers associated with the strike slip faults, we will see very briefly what we should look at. Okay. So there will be an offset of landforms, mainly what we see is the river or the terraces, river terraces, or we can say the floodplains, okay, of the rivers and all that. So in geological terms, we have classified that what all different landforms will see will not go into that much of detail, but few of them. Okay, like for example, what we will have, we'll see in terms of if there is a strike slip fault, we'll see a linear valleys, formation of the linear valleys along the fault. Then we will have offset of streams. Okay, so suppose the stream is flowing like this, okay, and then fault is crossing here, and then suppose there is a right lateral displacement of the fault. Okay, then what will happen? We will see the streams are coming like this. Okay, if you remember, I will have talked this when I was showing a slide on the San Andreas fault. Okay, so this is what will happen, and along with this, the landforms will also get displaced. Okay, which will result into the formation of the sac ponds, result into the formation of the linear ridges. Okay, so these are the, and of course we will have the scarps also. Okay, so this is what the most important features we will be able to see along the strike slip. We will continue in the next lecture. Thank you so much.